Hello everyone, I hope you're having a good day. Today we're going to be talking about simple trusses. I'm going to be presenting a method of solving simple trusses, of analyzing simple trusses. That's the method of joints. And the information will be from this textbook, so feel free to glance at that if you want. First, we'll talk about three important engineering structures. So those are trusses, frames, and machines. So each of these have stationary members. Well, not all of them have it. Trusses do, frames do, while machines don't. The number of multi-force members in each of these are different as well. Trusses have 0 multi-force members, frames have greater than or equal to 1 multi-force members, and likewise for machines. The design intent of each of these structures are also different. For trusses, they're designed to support loads. Frames are also designed to support loads, but machines are designed to transmit or modify loads. The number of members connected are different for each of these. For the trusses, only their ends are connected, while frames can be connected anywhere and machines can also be connected anywhere. For typical trusses, here are our typical trusses. We have a few types of roof trusses over here, and typical trusses continued, more typical trusses. So no, not all these are simple trusses, like this one, the Baltimore Ridge truss, the Baltimore Bridge truss. So basically, we'll be talking about some trusses. This is a poorly designed truss that cannot support a load. This one over here is most elementary rigid trusses that are consisted of a simple triangle. This is a larger rigid truss built up from the triangle B, and this is a rigid truss not made up of triangles alone. So we'll talk about simple trusses. Simple trusses are a very important type of truss. The construction method of a simple truss involves adding 2 new members to 2 existing joints, B and C over here, as you see, and connecting them at a new joint called D. These 3 joints must not be in a straight line. A simple truss is not necessarily made of only triangles. This is an example of a simple truss that is not made of triangles. We can trace starting at, for instance, BD. We draw 2 lines and connect it at a new joint C. From the 2 joints, existing joints CD, we can draw 2 new lines and connect it at a new joint F, and so on. But this is not a simple truss, as we talked about before. So trusses, what are they used for? Well, they're used for bridges and buildings and other stuff. We can see example of trusses in this bridge over here and in this building construction over here. So let's focus more on this, the trusses in this roof. The components of trusses, well, trusses consist of straight members connected at joints. So if we focus on only this portion of this roof, we can see that there are 3 members in yellow and 3 joints in blue. The same triangle below. The yellow one we will call members, and the blue ones we will call joints. Now there is a simple formula for finding the number of members for a simple truss. For a simple truss, the number of members is equal to 2 times the number of joints minus 3. As we can see here, it works out perfectly. We have 3 members, and that is equal to 2 times 3 joints minus 3. Basically, truss members are connected at extremities only. No member is continuous through a joint. So as you see, these are the joints, and then there is no member AB, but instead 2 distinct members, AD and DB. Most actual structures are made of several trusses joined to form a specific framework, as you can see in this roof above. Truss 1, truss 2, truss 1, truss 2, truss 3, truss 4. Each truss is designed to carry loads that act in its plane and thus may be treated as a 2D structure. Modeling trusses. A typical truss consists of straight members connected at joints. As you can see here, these are the joints. We can model a truss as two force members connected by pins, replacing those joints by pins. How a truss is loaded? Well, a truss can be in tension or compression. A two-force member of a truss can be in tension or compression. Load application. So basically, in general, the members of a truss are slender and can support little lateral load. All loads, therefore, must be applied at the various joints and not to the members themselves. When a concentrated load is to be applied between two joints, or when a truss must support a distributed load, as in the case of a bridge truss, a floor system must be provided. As in the diagram above, the floor transmits the load to the joints through the use of stringers and floor beams. Here is a portion of a real bridge superimposed on this diagram for you all to see. Load application. We assume that the weights of the truss members can be applied to the joints with half of the weight of each member applied to each of the two joints the member connects. Although the members are actually joined together by means of welded, bolted, or riveted connections, it is customary to assume that the members are pinned together. Therefore, the forces acting at each end of a member reduce to a single force and no couple. This enables us to model the forces applied to a truss member as a single force at each end of the member. We can then treat each member as a two-force member, and we can consider the entire truss as a group of pins and two-force members. Forces that tend to pull the member apart apply tension forces, while forces that tend to push the member together are compression forces. We can use the method of joints to analyze trusses, the forces in trusses. Trusses can be considered as a group of pins and two force members. Dismember the truss and draw a free body diagram for each pin and each member. Each member is acted upon by two forces, one at each end, and these forces have the same magnitude and the same line of action in opposite sense. Furthermore, Newton's third law states that the forces of action and reaction between a member and a pin are equal and opposite. Therefore, the forces exerted by a member on the two pins it connects must be directed along that member and be equal and opposite. The common magnitude of the forces exerted by a member on the two pins it connects is commonly referred to as the force in the member, even though this quantity is actually a scalar. Because we know the lines of actions of all the internal forces in a truss, the analysis of a truss reduces to computing the forces in its various members and determining whether each of its members is in tension or compression. So let's talk about some sign convention. In truss analysis, a negative member axial force implies that the member or the joints at both ends of the member are in compression, while a positive member axial force indicates that the member or the joints at both ends of the member are in tension. Let's talk a little bit about the line of action, what that specifically means. Here's a diagram. When you have a R length and a point of application, we apply the force at that point of application, and the force has a line of action connected to the moment arm. So torque is another name for a moment. It's equal to the cross product of the R length times cross the F, the force. And basically we're saying that that is equal to the magnitude of the force times R times sine theta. And in other words, it's F times R perpendicular. So that's an alternative way of understanding that. As you can see, it connects on the line of action, and basically F times R sine theta means that we only want the y component of the F force, because only that is producing a moment. Only that part of the force is helping to turn this structure. This entire structure represented by this. So now we'll be working through an example problem. Using the method of joints, determine the force in each member of the truss shown. State whether each member is in tension or compression. Okay, let's jump right in. So first we want to draw forces at each member or at each member or joint and apply Newton's third law, as we saw. Because the member and the exerts a force on the joint, and the force and the joint exerts on the member that same force in the opposite direction by Newton's third law. We don't know which members are in compression and which are in tension, but I drew these directions after solving for each of the force directions in the following slides. So this is like kind of a summary diagram after all the hard work I did. As you can see, focusing on each of the members, member CE, this is a Newton pair force. And then member DE, also a Newton pair force, except this one is in tension. Member CD, which is in compression, a Newton pair force. Member BD, in tension, a Newton pair force. Member BC, in compression. Member AC, in compression. Now we also have reaction forces at A and B that we can break up into their X and Y components. Assume the reaction forces at A and B have both an X and Y component. Now we can see all the forces over here. All the forces we need to solve for. Maybe not all of them, because we don't really need to solve for AY and BY, as we will see later. How is trusses loaded? As a reminder, a two-force member of a truss can be either in tension or compression, but always assume first that it is in tension. The force will be positive for tension and negative for compression. Joint E. First, we'll start our analysis by analyzing joint E. Assume that member DE is in tension, so if the force of DE is negative, we know that it is in compression by sign convention. Do not use the law of signs, as that would make compression and tension ambiguous, because it will always give you a positive value for F, as you can see here. But it's good to note that often it is easy to predict whether a member is in tension or compression by using force triangles, as you'll see later. We have the force FD over here, which we assume it is in tension. We draw that. And then we know that thus the direction of FEC must point to the left for the force triangle, for all the forces in the force triangle to add to 0. Use triangle equilibrium to be assured of the right directions of force arrows and tension or compression. So FE is equal to the magnitude of FE times the unit vector along the line DE, as you can see here. And that is equals to the magnitude of FDE times 15 over 17, and for the X component, and times 8 over 17 for the Y component. FEC is equals to the magnitude of FEC times the unit vector along EC, and that is a unit vector pointing at -1, 0. 24 kilonewtons is equal to 0, -24. As you see here, that's the vector. These are the unit vectors, except for the 24 kilonewtons, that isn't actually a unit vector. Because the magnitude of that vector isn't 1. So just ignore that part. So these are the unit vectors, vector 1, vector 2. And then the final vector isn't a unit vector, but it's the vector in the direction of the force, this one. The sum of the forces in the X direction are equal to 15 over 17 times the magnitude of FDE minus 1 times the magnitude of FEC plus 0, and that is all equal to 0 because this is in equilibrium. And the sum of the Y forces are equal to 8 over 17 times FDE magnitude plus 0 minus 24, and that is all equal to 0 because this whole structure is in equilibrium as well. That gives us that the magnitude of FDE is equal to 51 kilonewtons. And that FDE as a vector is equal to 45, 24 because of this equation over here. So the plugging in FDE for and the sum of the X forces we can solve for the magnitude of FEC. The magnitude of FEC is equal to 45 kilonewtons. That gives us that FEC as a vector is equal to negative 45 comma 0. As we can see here, because plugging in to that equation. So for joint D, we're going to be focusing on that now. Assume that member BD is in tension. So if FBD is negative, we know that it is in compression by some convention. Here's FBD. We need an arrow pointing these ways for equilibrium. And keep in mind all the forces again. Basically, why does FED point in that direction? Because remember we solved for FDE, which is this vector over here. And since FDE and FED over here must be a new impaired force, we know that FED points this way. So we can draw the vector in this way. FED, there you go. And FCD as a vector points from D to C. So we now have the unit vectors along DE, C, DC, and BD. These are the unit vectors. So basically we have FCD as a vector is equal to the magnitude of FCD times the unit vector along CD, which is 0, 1. FBD as a vector is equal to the magnitude of FBD times the unit vector along BD. And that is equal to that. And FED as a vector is equal to negative FDE. And that is equal to negative 45, negative 24 from what we solved previously, because in the previous slide we solved for FDE. So the unit vectors 0, 1 is this unit vector, the second unit vector along BD. And this third vector over here, this third unit vector over here is from this equation, is from FDE, except we is the negative of the unit vector along DE. So the sum of the forces along the x direction is equal to 0 plus 15/17 times the magnitude of the force FBD minus 45 kilonewtons, and that is equal to 0 since this whole structure is in static equilibrium. So that gives us that the magnitude of FBD is equal to 51 kilonewtons. So FBD is as a vector is equal to 45, negative 24. As we can see over here. The sum of the forces along the y direction is equal to the magnitude of the force CD minus 8/17 times the magnitude of the force BD minus 24 kilonewtons, and that is equal to 0. That gives us that the magnitude of the force CD is equal to 48 kilonewtons. So that FCD as a vector is equal to 0, 48. We got that by plugging in the magnitude FCD into this equation. Now we will be focusing on joint B. To solve for the force in member BC, that is the force BC, we must first solve for some reaction forces at components at A and B. Assume that the reaction forces have both an X and Y component. As we can see, here are the reaction forces at A and B again. The sum of the moments about B, that is equal to negative 24 times 6 plus 6 times sine of 90 degrees. As you can see here, because this is the R length and this is the 90 degrees. And we have to add the AX component times 4.5 meters times sine of 90 degrees because of the line of action. So basically the line of action is if we draw this force out over here, and then we note that our length, the distance to the B is 4.5. So that is using the line of action. This is the line of action. And that is equal to 0. The sum of the moments must be equal to 0 because this whole structure isn't turning. So it's in static equilibrium. For static equilibrium, we must have that the sum of the moments is equal to 0 and that the sum of the forces is equal to 0. The line of action makes the distance A from B 0. So we use the X component of the A reaction force and not the Y component of the A reaction force, because the Y component of the A reaction force doesn't gives us 0 moment. The moment is simply 0. So yeah, as you see, we used AX. So AX is equal to 64 kilonewtons after solving for AX from that equation. And then remember this review of line of action and the point of application, what line of action actually means. Now the sum of the moments about A is equal to the X component of the B force times 4.5. As such, minus 24 times 6 plus 6. So why 24 times 6 plus 6? It's because we can move the line CE up like this, and that total distance is 12 meters, and move the force along its line of action up like this. And the sum of the moments about A is also equal to 0. So we can find that Bx is equal to 64 kilonewtons as well from rearranging that equation and solving for Bx. So joint B, again, assume that the member BC is in tension. So if the force BC is negative, we know that it is in compression by sign convention. BD forces acting on B. The free body diagram of all the forces acting on B is seen below. We have FBC, FDB, and the reaction force at B. They're all acting on the point B. The sum of the forces along the x direction is equal to Bx plus FBC plus FDBx, the x component of FDB, that is, and all that is equal to 0. We know that Bx is equal to 64 kilonewtons as we solved just previously, plugging and that the force FBD is equal to 45 comma negative 24. So we know that FBDX component is equal to 45 kilonewtons, and that FDBX component is equal to negative 45 kilonewtons. So plugging all those in, we have 64 plus FBC minus 45 is equal to 0. Solving for FBC, we have the FBC is equal to negative 19 kilonewtons. So that means that it's in compression in the joint A. Assume that the member AC is in tension, so if FAC is negative, we know that it is in compression by sign convention. The free body diagram of the forces acting on A. So as we see, we have the forces FAC and the reaction force at A acting on A. We have theta between AC and BC. So the sum of the forces along the x direction is equal to the x component of the A force, the A reaction force plus the force AC times the cosine of the theta, and that is equal to 0. So the known information, so we saw for AX earlier that is equal to 64 kilonewtons. Theta is equal to arctan of 44.5 meters over 6 meters. And thus plugging in all the known information, we have 64 plus force of AC times cosine of theta, and that is equal to 0. So the force of AC is equal to negative 80 kilonewtons. So that implies that it is in compression. Thank you guys so much for watching this video. I really hope that it helped you in your statistics endeavor and helped you understand the analysis of trusses, simple trusses, using the method of joints. Stick with me for the next video.